couple of seconds, we can start with the introduction. Okay, so it is my great pleasure to introduce Stephen Wright. So Stephen Wright holds the George Dantzig Professorship, the Sheldon Lubar Chair, and the Hammer and Biden-Soy Professorship of Computer Sciences at the University of Wisconsin-Madison. His research is in computational optimization and its applications to many areas of science and engineering. Prior to joining the University of Wisconsin-Madison in 2001, Wright held positions at North Carolina State University, Argonne National Laboratory, and the University of Chicago. Wright is the author and co-author of widely used reference books in optimization, including primal dual interior point methods and numerical optimization. He has published and is currently keep on publishing very widely on optimization theory, algorithms, software, and application, and is the current editor-in-chief of the SciAm Journal on Optimization. We are really glad that he's joining the summer school, and we are very much looking forward to his talk. He will share with us his views on learning, control, and optimization, and how these three disciplines are interconnected, and what are the fundamental achievements and future steps we should be taking. Professor Wright, many, many thanks, and the floor is yours.
Thank you so much for this invitation. Good. It looks like my screen is there. So it's a real pleasure to talk here. And I'm just sorry I couldn't join you in real life. I haven't traveled in the last 18 months at all, and I really would like to at some point. So you'll notice me looking down because I've got an iPad here and I'm going to be writing on the slides, and it's sort of in front of me, so it's hard for me to make eye contact, but so I hope you'll excuse me. So I just have a few words about a variety of topics at the interface of these three areas. Here's a summary of what I'll do. I'll start with some overview of some interactions between control, learning, and optimization. Learning, you could also call that by other names. Data science is becoming maybe a more popular, more inclusive term. I'll say a little bit about some recent work that I did with Pratyush Kumar and Jim Rawlings at University of California, Santa Barbara on applying neural networks to model predictive control at an industrial scale. I'll talk a little bit next about some new perspectives on non-convexity. In optimization, we used to think that finding global solutions of non-convex problems was impossible, but now it turns out there are many non-convex problems where that's not so difficult. And I'll talk quite a bit here about, there's a stream of very recent work in the machine learning community about why are OverParametrized neural networks so effective. And there is starting to be some theoretical understanding emerging of that phenomenon very recently, just in the last 2 or 3 years. So I'll say a little bit about one of the streams of work in that area, because I think it's a very important one. And lastly, I'll talk about something that kind of involves all three areas. It's some work that we did in 2017, 2018 to analyze the convergence of stochastic optimization algorithms for learning, but using techniques from control, actually techniques that you probably learned about earlier today in the sessions with Professor Allgaier. So let me dive into the first topic. So first of all, just focusing on optimization and control. Well, there's been a lot of interaction between optimization and control for many years. There's actually a SciAm Journal on Control and Optimization that I think was founded way, way back in the 60s or 70s. So it sort of addressed both topics at once. I sort of came into the area about 30 years ago because I had a colleague in my first job that worked on both things. And I sort of took the viewpoint of someone that was trained in optimization. I said, well, here are these control problems, MPC, LQR, open loop control. These are just optimization problems with a lot of nice structure and a lot of cool properties. And also you need efficient algorithms because you need to solve them in real time. So that was my kind of very parochial, narrow-minded viewpoint of control. But of course, control people have a more mature, broad perspective on this. They don't just want to get optimality and fast solutions. They want to prove things about the stability of the controller. They want to be able to use solutions that maybe are not optimal, but are at least feasible and will give you stable control and so on. They know that optimization algorithms and perspectives are useful, but they've also got their own sort of collection of algorithms. So there are two slightly different viewpoints, but the intersection between them is very large, and there's still a lot of ongoing interactions. I'll say more about this in a moment. Now, also the interactions between optimization and data science, machine learning, of course, these have become a very big thing in the last 10, 12 years, but they actually go back a long way. And my colleague here in Madison, Olvi Mangasarian, he passed away just before the COVID lockdown started, but he actually did work in the early 1960s on classification using linear programming. And this was before he worked in academia. He actually worked for Shell back then, the oil company out in California. And he published these papers about pattern separation using linear programming. And he continued to work on this for the rest of his career, different aspects of machine learning, right until until the end of his life. So that was, that's a very long-standing connection. But starting in about 1998, that's when I first heard about these connections, because people in machine learning came to me with kernel learning problems, linear classification, and then kernel learning, the generalization of that. And they had their own algorithms that were sort of, you could interpret them as optimization algorithms, but also they started to use duality in a very imaginative way. And so starting around that time, 1998, 2000, the connection between optimization started to be made. And then since about 2008, it's really taken off. And now there's a tremendous amount of interaction between those two areas. So here's something I found on the web about 3 years ago, but I checked a couple of weeks ago and it was still there. This is this company called SAS. And they have this thing called machine learning cheat sheet. So this is for people who are coming in with some sort of data science problem and they're not sure what kind of problem it is and what kind of algorithm they need to solve it. So when I was writing a talk, actually for a talk in Braunschweig 3 years ago, I found this and I looked at it and I realized that an awful lot of the algorithms that they talk about here are actually optimization methods. So all the ones in yellow ovals are basically optimization approaches. You could argue about some of them. I mean, SVD and PCA are really sort of linear algebra, but if you want to do them in a sparse way, you need an optimization formulation. But other things like kernel SVM, training neural nets, gradient boosting, logistic regression, these are all optimization methods. And I even argue that some of the ones with red circles, which I'm not claiming as optimization methods, some of them actually do use optimization techniques as well. So the theme is that a lot of the algorithms, a lot of the formulations that you use in machine learning are really optimization formulations. In fact, I'd say that optimization is kind of the major source of algorithms in machine learning and data science. And why is that? Well, formulating something as an optimization problem forces you to think rigorously about the different trade-offs between the goals of what you're trying to do. They allow you to translate statistical principles like likelihood and significance into mathematical formulation, mathematical equations or inequalities that you can then incorporate in a formulation. Basically, the formulation process forces you to sort of think about all these trade-offs and to make things sort of concrete, what you're trying to do. And then optimization algorithms, of course, there's a whole suite of algorithms that you can use to solve these formulations. Now, the thing about learning is that you don't usually do well if you just take a standard optimization method in a package like Gurobi and just apply it out of the box. You often have to tweak it to make it work. And why is that? Well, first of all, you have to take account of the context and the structure of the problem. By the context, I mean, do you really need a highly accurate solution, or are you going to be happy with a feasible solution that you can find rapidly that might be a little bit suboptimal? And another issue that comes up a lot in learning are so-called hyperparameter tuning. And what they typically mean by that is just choosing the step length in the algorithm. That can be a major issue. And there can be other parameters in there as well. And there are, dozens of people at Google whose job is basically tuning hyperparameters. So it's a really big deal. Another thing that I mentioned here is duality. I'm not going to say any more about that, but that was realized very early on in the late 90s, that if you took the kernel learning problem, the perspective of duality was extremely important in formulating that problem in a way that you could solve it. And then non-smoothness. This is something that not many of us in optimization paid much attention to. There were algorithms for non-smooth problems, but their convergence was very slow. But it turns out that non-smoothness is actually very common in formulations of data science problems, but usually it appears in a highly structured way so that you can incorporate it in algorithms pretty easily. And I just mentioned here that there's starting to be more involvement of discrete optimization in learning. It's always been on the edges, but of course, discrete optimization problems are typically a lot harder to solve. But recently, the state of the art in that area is getting better and better in terms of the speed of solvers for integer programming. So they're becoming more and more, it's becoming more and more feasible to at least consider using discrete optimization forms. A little bit more about the interaction between optimization and learning. This is something that I've been working in for quite a few years, so that's why I'm sort of focusing on more than other things. But it's certainly true that the needs of the machine learning community have influenced optimization research very much in the last 10 years or so. And the priorities of machine learning people, when they solve their optimization formulations, they're not exactly the same as our traditional priorities in optimization. We're sort of interested in finding a highly accurate solution. We're happy with local solutions. We don't care that much about the global convergence rate. We do care about local convergence rates and so on. That's in optimization. Machine learning people have a different perspective. Machine learning is heavily influenced by theoretical computer science. So they like to think about issues like computational complexity, upper bounds on the amount of computation an algorithm will take to solve a certain class of problems. They're interested in global convergence rates. They don't care that much about local convergence, whether an algorithm is superlinearly convergent or quadratic convergent. They don't really care. And they're also not particularly interested in getting highly accurate solutions, because usually the problem that you're solving is an empirical representation of some real problem, and you only really need to solve it to within statistical accuracy. Anything more than that is kind of a waste. And so they don't really care at getting a solution that's accurate to like 8 digits of accuracy. They'd much rather find something that was cost less to find and was accurate only to a level of 1 over n or something, where n is the number of training points. So all that said, machine learning and data science have made very heavy use of optimization techniques in the last 10 or 12 years. And these are sort of an example of things that they've been working on. Probably far and away the most important of these is the first one on the list, stochastic gradient. That's what's used to train neural nets in various forms, various enhanced forms, but that's far and away the most kind of occupying the most compute time. If you looked at all the compute time was being used to solve data science problems, SGD is maybe 99% of that. But people in learning have also got very interested in Nesterov accelerated gradient approach, which is a variant on steepest descent, just uses gradients, but does it in a very clever way that produces lower complexity. The conditional gradient approach of Frank Wolf dates back to the 1950s. It was rediscovered maybe 12 years ago or so, and it turns out to be very useful in several machine learning applications. The idea of scaling the gradient by using clever sort of information to scale the components of the gradient. There's this paper by Adam, and I've given up counting how many citations it has because seems to grow about 1,000 a day. But that turns out to be the variant. When people call a stochastic gradient package, they usually call it with Adam. And then maybe a little bit before the modern era, a lot of us optimization people worked on compressed sensing and sparse regularized optimization. That's starting about 2005 through early 2010s. And this was optimization problems with non-smooth regularization terms. So we had to use a lot of algorithms in that space. And then there's also been some work in sample Newton and quasi-Newton methods. Not that much. People have been trying these over and over again. They typically haven't been competitive for practical problems with stochastic gradient, but we haven't given up hope that there'll be applications where second order, higher order information will be useful. Recently, there are some other topics that have sort of made their way from optimization into learning. One actually goes back some way. Matrix optimization or matrix optimization problems in machine learning go back to about 2008 with a paper by Wright, Fasel, and Perillo. And then it was discovered by, way back before that, by Bureau Montero, that you could use a non-convex low-rank matrix formulation and solve large-scale versions of matrix learning, matrix optimization problems. And now they've become ubiquitous, those kinds of formulations. Also, maybe about 7 years ago, people in learning discovered trust region methods. I'm currently revising the chapter in my book with Nossadal on that topic because it's turned out to be interesting again, particularly in non-convex settings. People have been interested in nonlinear conjugate gradient, Newton conjugate gradient. I've worked a lot recently on Newton conjugate gradient. Chi Jin and Michael Jordan and those people in that Berkeley group have worked on using steepest descent or gradient descent in non-convex settings, but they escape from saddle points. Saddle points are points where the gradient's zero, but they're not minimum. They're not local minimizers because there's some negative curvature in the second order term. And they've investigated algorithms that add noise to steepest descent in a clever way to escape from saddle points. And they can prove convergence and complexity result about that. And then this field of adversarial machine learning has been around since, I guess, 2013. This comes from the observation where if you train a classifier, a neural net classifier, but then you add very carefully selected small perturbations to the image or the speech that you're trying to classify, the network can give nonsensical results. And so there's interest in doing the training in a way that it's more robust to those kinds of perturbations. And robust optimization and bi-level optimization have been tools from optimization that have been used in that area. Some of you might know about that. So, but I guess it's my contention that the toolbox of optimization contains a even wider range of algorithms than I've talked about here. And I think in future, many of them are going to continue to be useful in learning. We're going to find applications that are going to draw on new or existing areas of optimization, like binary and integer programming, like semi-definite programming, for example. Now, semi-definite programming has been used in low-rank matrix problems. In fact, before people started using Bureau Montero, they used semi-definite programming formulations. But I don't think that the use of semi-definite programming has been exhausted. I think we're going to be finding other applications in learning going forward where semi-definite programming is useful again. So I think there are more optimization techniques that are going to be relevant somewhere in the future. I'm mentioning one thing. I ran a meeting last Thursday and Friday, an NSF PI meeting on their fundamental data science program. And I ran a panel where Michael Jordan from UC Berkeley was a panelist, and we asked for his perspective on what are going to be important major challenges in data science going forward. And if you've heard him speak in the last 4 years, you've probably heard him say that the interface between data science and economics is going to become extremely important. And he's got all kinds of reasons for why he thinks that's true. Data has a value, and principles of economics are useful in evaluating the worth of data and creating markets for data of different kinds. So he speaks very passionately to that topic, and he's doing a bunch of work on that topic with a number of different collaborators. But the reason I mention it here is this is a perfect example where here is a new sort of paradigm that people are exploring. And it turns out that there's an amazing collection of tools in optimization that precisely address this class of problems. Complementarity and variational inequality formulations are useful in modeling anything involving games, anything involving competing agents, which of course is what you've got in economic type problems. Bi-level and hierarchical optimization, the same thing. Stochastic optimization, where you've got to make decisions over a period of time, and possibly not just one set of decisions, but decisions, say, every day or every week. And you want to make decisions in such a way that you put yourself in a good position to be able to make good decisions in future time points as well. So these are a whole collection of algorithms that haven't yet been used very much in data science and machine learning, but there's enormous potential, particularly if you're interested in economic topics, to bring that in. And the reason is that the historical roots of optimization, going back to George Dantzig in the 1940s, they're very deeply rooted in operations research and economic decision-making. That's where optimization came from. And so that experience, I think, is going to be very useful if data science goes off in this direction. And not just optimization, but also control theory. I remember even when I was in high school reading tracts by Polish economists. This was during the Eastern Bloc era, where they talked about using control in an economic planning context. So, so I think control is relevant here as well. And here's a little anecdote. My colleague here at Wisconsin, Jim Rawlings, who I think many of you know is a very senior person in industrial control, model predictive control. We wrote a proposal in 2009, right after the financial crash of 2008 and during the Great Recession. And our proposal was to an engineering directorate, but we proposed to use NPC to do modeling in macroeconomics. We said, look, clearly these economists have no idea what they're talking about. They failed to predict the recession. They failed to agree on how to handle it. Give us a shot at sort of modeling this and coming up with some ideas. And the reviewers commented that, yes, clearly we're very passionate about this topic, but clearly also we had no expertise, and so they didn't fund the proposal. But I wish they had, because it would have been great fun to work in this. Okay, so let me say a little bit about learning and control. I'm not going to say much about this because, of course, this workshop follows on the heels of the L4DC conference, which is all about the interface between learning and control. So you will have heard a lot about that in the last 10 days or so. In fact, I think Michael Jordan spoke at that conference, so you probably heard him speaking on this topic that I was just discussing. You know, there are very strong connections here as well. You need data science learning techniques to identify models so that you can do control with those models. There's a tremendous outburst of interest in reinforcement learning. It's proved to be very successful in certain topics like playing AlphaGo and chess and so on. And its connection with control is a very, very hot topic in machine learning. And then there's this thing that I'll say a little bit more about, the connection between deep learning and explicit NPC. So let me talk a little bit more about that last topic. So back when I gave a talk pretty much along these same lines in 2018, papers had just started to appear by some of these, well, I'll get to that in a couple of slides, by these authors, Kagan, Lucia, Chen et al., 2018. I think there have been many more papers on this topic since then. And they sort of asked the question, can you train a neural net to implement an explicit NPC law? So what do I mean by explicit NPC? Just in case you're not familiar with that, here is classical linear quadratic model predictive control. So anyone with a background in control will have seen a formulation like this. X are the states, xt is the state at time t, ut is the input at time t. And so classically what we do in model predictive control is figure out what state we're in right now, solve this linear quadratic model going forward, and then use the U0 solution to this model as the input to the system. So you look out to a certain time horizon, You take the current state as your starting point. You solve this with a linear dynamics and a quadratic cost. You get an entire sequence of inputs over that time period, but you only use the first one, and you inject that into the system, and then seconds or minutes later, you go through the whole process again. So it was observed maybe 2010 or earlier by a number of authors, and I've listed some of them here, that the solutions of this system are a piecewise linear map from the initial state, or the current state of the system, which we'll call X naught, to the input U naught. So the whole process of plugging in X naught, solving this quadratic programming problem, and then pulling out the U naught, that essentially defines a piecewise affine map. And so rather than solving this quadratic programming problem online, you can calculate that piecewise affine map offline and just solve it as a list of inequalities. So that when you come along with state X naught, you just have to figure what part of the piecewise affine space am I in? And you can do that by evaluating a bunch of linear feasibility conditions. And then once you've figured out what part of the space you're in, you just have to apply a linear map and you're done. You've got the solution. So in other words, you do a tremendous amount of work to compute this map offline so that when you run it online, you can implement it very quickly. Now, the problem with this is that the number of pieces in the piecewise linear map, which we'll call J, that grows explosively with the horizon length and the dimension of the control and input spaces. It grows massively, so that really this is only possible to do if you've only got one or two states and inputs, one or two dimensional states and inputs, and N is quite modest. So to implement this practically, people made sort of several proposals, and there was a lot of work in sort of coming up with versions of this map, approximate versions of this map that had a lot fewer pieces. But people asked the question, even in 2018, neural nets, if we run neural nets with so-called ReLU nodes, the ReLU nodes are where the input to the node is clipped at 0. So if the input is V of any one of these colored nodes here, the output is going to be the max of V and 0. So you can use that to model an affine map. So in other words, what comes out of the top of the neural net is going to be an affine function, a piecewise affine function of what goes in at the bottom. So this seems like a good match to explicit NPC. So can't we use a neural net to learn an explicit NPC law? And of course you can. And so people in the control community actually figured out how many neurons do you need in the network, what depth of the network do you need in order to capture perfectly the explicit NPC map in a neural net. So it turns out that, of course, the size of the neural net is way too big, okay? If you've got J pieces in the neural net, you're going to need a neural net of depth J, and that's really not practical. But at least there was some sort of theory there. Now, this is 2018. I haven't really kept up with this literature since then. I suspect that people have made enormous advances, and I'm sorry, probably they've given talks during L4DC about this, and I'm sorry that that I'm not aware of later work, but I'm sure there is some later work on this. You know, these were the earliest results in this area, and definitely it was the right place to start. So Jim Rawlings and I, as I mentioned, Jim is at Santa Barbara, and his student Prachesh Kumar, we have a paper that just appeared very recently where, and I got to say, Jim and Pratyush did all the work on this. I was kind of mostly a spectator, but you know, our initial experiments in trying to use neural nets to replace solution of the quadratic program were not successful. We found even for small systems and even for large neural nets, we couldn't get the neural net to approximate the solution of the QP well enough. Until we sort of hit on this idea, and this, again, not my idea, this is Jim and Pratyush, they hit on this idea of sort of structuring the neural net so that it had some desirable properties built into it. And the property that we want is basically if the initial state X is already at its set point, we don't want to change the input. So in other words, if this is the set point XS, and if our initial state X0 is right at the input, we want to output a control U0 of 0, okay? So we structure the network so it doesn't change the input if the system is already at the desired state. That's the basic feature that makes this work. So let me walk through what else we sort of had to do to set this up to be reasonably successful. We assume that the plant is linear. We do allow disturbances to be present, but of course there are nice ways involving Kalman filters and so on to detect what the disturbance is. So first of all, we have a desired set point, USP, for the input. But given the disturbance, we have to possibly tweak that set point by solving a little QP, okay, to find out what's a feasible set point that's in the range of allowable inputs, where the state is also in the range of sort of allowable states. So we have to do a little bit of pre-processing with the disturbance to figure out what should be the state set point, what should be the input set point. So given that, we then set up this, conceptually, we set up this QP that looks at deviations around those set points. So the variables here are x tilde k, u tilde k, which are variations around US and XS. And so this is just an LQR problem that captures deviations from the current point. But we design a neural net to replace this solution of this quadratic program, but we design it in such a way that when the x tilde, when the current state is already at the state set point, it outputs 0 as a desired input, okay? So in other words, the neural net is parameterized by these weights theta. So the weights are just all those matrices that capture the transformations between successive layers of the neural net. The other inputs are the state set point, the control set point, and the current state x, okay? And then we define the output u0 to be the difference between the output of the neural net when we plug in the current state being xs and when we plug in the real current state, x hat. So if x hat equals xs, u tilde naught is going to be 0, which is what we want. If x hat's different from xs, u tilde naught is generally going to be something else, either positive or negative. And then we use that as the input to the system. So as you know from learning, you have to train the neural net to behave in the same way as the solution of the quadratic program. Now, of course, I've already told you that once the parameter and input space gets large, trying to train the neural net so it works well on the entire space, you're going to need an incredible amount of data. It explodes exponentially in the dimension. But we sort of use the observation that realistically, set points and disturbances stay within a much narrower range. They don't span the whole parameter space. And so we just sort of figure out what are realistic ranges for set points and disturbances and just train randomly in that space. There's a little bit of theory, but I'll just go through one of the experiments. This is an experiment on a fair-sized problem. It's a distillation unit, a standard problem in the MPC literature, 252 states, 32 controls. There are 90 measurements made of the states, and this is a pretty long control horizon, okay? So to set up that quadratic program that I showed you earlier that's traditionally solved in MPC, to solve that takes about 30 seconds. And that's okay in this setting because you don't need to change inputs that much, but it's still a significant amount of time, 30 seconds to solve the MPC subproblem. So we instead trained a neural net to sort of imitate the quadratic program. We needed about 360,000 training samples. Just generating those training samples, we had to, that means we had to solve 360,000 quadratic programs to figure out what the output was or what the appropriate input was for a given initial state. And that took 28 hours to do on a small cluster of computers. We tried neural nets with 3 layers and about 2,000, width about 2,000. And the upshot here, there are many more results in the paper, but this is just one of them. The upshot here is that we could get within 1% of the performance of traditional MPC based on solving a quadratic program, within 1% of that in terms of measuring some objective of performance. So basically doing just as well as the real QP. But the interesting thing is that it only takes about 0.003 seconds to produce the appropriate input for a given state. That is, once you've trained the neural net, which takes an enormous amount of time, you have to take all 360,000 training samples, you have to call Adam and a standard training package like PyTorch to train the weights in the neural net. But once you've done that, actually deploying the neural net is incredibly fast. It takes about 1/10,000th as much time as solving the QP. So this was a distribution of how much time it took to solve the QP. You can see about 30 seconds. And for the 3 neural nets, it's down here around about 0.003 seconds. So much, much faster. So it turns out that you can do this, at least in our experience, on reasonable sized plants. And it might be a way forward, particularly when you need to control the plant frequently, when you need to, when you only have a very short time between decisions. Okay, so I guess I've got about 25 minutes left. Yeah, that's good. So let me get into the next section of the talk, which is about non-convexity. So as I mentioned earlier, if your goal is to take a general smooth function and you want to find its global minimum over a domain, that's an extremely difficult problem computationally. Its difficulty blows up exponentially in the dimension of the domain. So, you know, traditional optimization, we kind of thrown up our hands and said, this is impossible. Let's just try to find a local solution, a local minimizer. So that's what we've done traditionally. But in the last few years, particularly in the last, 5 years or so, maybe 10 years in some areas, people keep stumbling across important non-convex problems in learning, but also other areas that are actually pretty easy to solve. Despite the non-convexity, you can find a global solution and you don't have to do anything special. You can just run a standard method like gradient descent. And here's a list of problems where that's true. So this Bureau-Montero low-rank parametrization of matrix optimization, definitely non-convex formulation, but if you run gradient descent on it, it'll pretty much always get the global solution. And there are reasons for that. There are analyses that explain why this is true. And this is a review paper with some of that analysis. More recently, people have shown that tensor problems, going beyond two-dimensional matrices to higher order tensors, 3 dimensions and above, again, low-rank decompositions in tensor applications have the same property. Despite the non-convexity, you find solutions. Emmanuel Candes started working on phase retrieval problems in around 2015. Nicolas Boumal, who I think is talking next in this meeting tomorrow, worked on phase synchronization. Again, both non-convex problems. Again, finding a solution doesn't seem to be too difficult. AC power flow, very important class of problems in modeling power grids. There's a very recent work just from a couple of months ago by Stephen Lowe and his collaborators. In fact, I gave a talk on the topic of complexity of non-convex optimization at Caltech 3 weeks ago, and Lowe was in the audience and he pointed out this new reference to me. The dictionary learning problem, a problem from machine learning, non-convex, but again, pretty easy to solve. And probably most surprisingly of all, and I'm going to say a lot more about this now, is that neural networks fall into this category. Over-parametrized neural networks, they're really the training problem that you have to solve to make the weights in the network be such that the input matches the desired output, are extremely nasty, non-convex, non-smooth problems. And yet, if you run gradient methods long enough, they'll find a solution. And I'll say more about that. They'll find a global solution. So a little bit about what's going on here. What's happening that's making these non-convex problems so easy. And just stepping back, I would say that conventional wisdom in continuous optimization, I really seen it evolve even during my career. So back, I'd say up to the 1980s, people perceived the great divide. If you're doing a taxonomy of continuous optimization and you had to decide, okay, at the top level, when you take continuous optimization, what's the most fundamental split that you can make to split it into 2 categories? And up to the 1980s, people would have said, well, linear versus nonlinear, that's the most fundamental distinction. But then interior point methods came along, Kalmakar's method, primal dual methods. They basically used nonlinear optimization techniques to solve linear programming. So that sort of blurred the dividing line between linear and nonlinear. And then I'd say from the 1980s through the 2010s, the great divide was between convex and non-convex. And that came partly out of the Nemirovsky-Uden book on complexity of convex optimization from 1983, where they said in that book, they basically say, non-convex, forget about it. We can't say anything about complexity. Let's just focus on convex. And then Boyd and Vandenberg have their book from the early 2000s that basically adopts the same viewpoint. Their book is called Convex Optimization. But now I think that conventional wisdom is changing again. Now we're sort of seeing the great divide in continuous optimization is between non-convex problems that really are hard to solve and everything else. So everything else includes convex optimization and non-convex problems that are easy to solve, okay? But how do we make the distinction between the easy non-convex problems and the hard ones? Well, there are certain structures and properties that people note in these easy non-convex problems that seems to be the properties that make them easy to solve. Here's one that you see in some learning applications. All the local minima, sometimes all the local minima are actually global solutions. They all have the same objective value. There are matrix optimization problems like that. The second property that some of these problems have is that, yes, they're non-convex. Yes, there are stationary points where the gradient's 0. But all of those points, they're either global solutions or they're saddle points. They're strict saddle points where the Hessian has negative curvature. And that's an important property because if the Hessian has negative curvature, you have a way of escaping from those saddle points. You're not going to get stuck there. There are also problems, and we'll see one of these in a moment, that have this so-called PL condition, Polyak-Lovisevich. And it basically says the gap between the current function value and the optimal function value is bounded in terms of the norm of the gradient squared. There are problems with that property. And that's incredibly important property because as long as you've got an algorithm that drives the gradient to 0, and gradient descent does that, for example, then simultaneously you're going to be driving f of x to its optimal value, its globally optimal value. So problems with this property, global optimization is going to be easy. There are a bunch of problems in matrix optimization that have a slightly more complicated property. I won't say too much about that. And then another thing that happens is that a lot of these problems, these easy non-convex problems, there are clever ways of initializing them. There are ways of looking at the problem, doing something clever, using statistics, using singular value decomposition or something that give you an initial point, x naught, that's pretty close to the global solution. And so if you just start running gradient descent from that initial point, you'll find the global solution. So I just want to stress here, I'm not talking about convex relaxations. I'm not talking about taking non-convex problems and embedding them in a convex problem and then solving the convex problem. What I'm talking about is just taking the non-convex problem as it's written, not doing anything special to it, just taking that problem, maybe doing something clever to find an initial point, but after that, just running a standard non-convex algorithm on it. And you will
excuse me.
I guess you want to write non-convex instead of non-linear, right?
Yeah, I mean to say non-convex, yeah. Yeah, so non-convex is something, convex is a function like this. Okay, non-convex is a function like this. Okay, so, in non-convex applications, you've potentially got a lot of local minima, but finding the global minimum, this one here, is potentially difficult. Okay.
Yeah, I'm just asking the last sentence. So I just want to make sure.
Yeah, sorry. Oh, I see what you're saying. Yeah, this should be non-convex. Thank you. Okay, I'll try to correct that later on. Thanks. Okay, I want to say a little bit. I guess I've got about 15 minutes left, about OverParametrized neural net. So I told you that this is a very hot topic. Understanding why neural nets are, first of all, so effective in certain applications, but also understanding why the problem of training them, while it's non-convex, it actually turns out to not be a very difficult non-convex problem. Not very difficult. It still takes a long, long time to train it, but if you run it long enough, you will find a solution that actually perfectly fits the training data. Okay? So this is true provided these neural nets are over-parameterized. And nowadays, I would say probably for most applications, people use over-parametrized neural nets. That is, they make them wide enough and deep enough so that the total number of parameters in the neural net is more than enough to fit the training data. The number of parameters often exceeds the amount of training data by, an order of magnitude or more. So one consequence of over-parametrization is that there's actually a manifold of solutions. There's not just a single set of weights that will perfectly fit the training data. There's an entire, very complicated geometric sort of manifold of weights that have that property. I put manifold in quotes because there's nothing smooth about it. It's got all kinds of kinks in it, but it seems to have a sort of a space-filling property that that the more you over-parameterize, the more this manifold seems to fill the space, fill the parameter space. But that's another topic. I won't get off on that. But as I've been saying, if you run it long enough, you can interpolate the training data. But the other surprising thing is not just that, not just so you can find a global solution, but the solution that you find has a good generalization property. That is, if you come along with a new piece of data that's drawn from the same distribution as the training data, it generally does a good job of predicting the output for that piece of data. So in other words, you don't overfit to the training data. So that's surprising as well. This phenomenon is called implicit regularization. Somehow running gradient methods on over-parameterized nets, even to global optimality, doesn't overfit the training data. It gives you something that generalizes well. So there's been a lot of work on this in the last 4 or 5 years. One of the foundational papers is this one by Moritz Hart, Ben Recht, Oriol Vignal, Sami Bengio, and Zhang, I think, were the authors. And they showed that over-parameterized nets trained to zero loss don't seem to significantly overfit the training data. They still have good prediction properties. There was some early theory from 2018, 2019, showing that if you ran a gradient method on a neural net with a single hidden layer, it reliably would find a global solution, and they could explain why that happened theoretically. Sort of a related topic is this double descent idea, which I'll say a little bit more about due to Belkin, which explains why over-parametrization is not a bad idea. And then there are these recent review papers that are actually going to appear in Active Numerica, both of them. And I was on the board, so I invited these papers, and they turn out, I think, to summarize the state of the art very well. So a little bit about double descent. Probably many of you have heard of this idea. Basically, it says that adding extra parameters to your model doesn't necessarily give you something that overfits. You can still get a very good classifier from an over-parameterized model. And I'm a little bit short on time, but I think I'll go over this anyway. So typically what we do in learning is that we've got a bunch of, we've got an underlying data distribution P. We don't know the whole distribution. What we do know is a bunch of training points selected from that distribution. So we try to find an empirical function, which is a mapping from the inputs X to the outputs Y, that does a good job on these training points, okay? And then we want to know, is that function going to do well on the rest of the data space P, okay? And the big question is, how rich do we make the space H that we select that function from? This class H that we're going to allow, we're going to restrict the function fmp, the empirical classifier. How rich do we make that space? Do we make it an under-parameterized space? Do we add a whole bunch of parameters, make it a richer space, whatever? And the classical regime that we looked in was this regime here. We only considered up to the point where we could perfectly fit the training data, where we just added enough capacity to the space that was able to interpolate the training data. So this dotted line, which is the optimal training error, goes to 0 at exactly the point where we've reached the appropriate capacity to fit the training data. But then what we're really interested in is this is the solid line. The solid line is how good a job is that empirical function doing at classifying unknown data. So when we're down here, the empirical function actually does a great, it's pretty much as good as the best possible function from that class. Now, when we're in this regime, we've got a very under-parameterized model. So the empirical function does as well as you could possibly do on that class at classifying unseen data. But unfortunately, because the number of parameters is so low, the risk is still pretty high. On the other hand, when you're out here, when there's a large number of parameters in the model, the empirical loss is doing terrifically well on the training data. Unfortunately, it's diverged a lot from the optimal risk function. FEMP is no longer a good estimator of the best possible risk function. So it does very badly on test data. So there's traditionally, there's been some sort of sweet spot somewhere in the middle of this regime where you add just enough capacity so that you get the empirical function does pretty well on the test data as well as on the training data. But what Belkin said was, well, what if we look beyond this point? Where if we, after we interpolated the data, what if we continue to add capacity to the function space and look to find the best possible function in that augmented function space? Possibly we can do better at fitting the test data or the data from the underlying set as well as the training data. And it turns out that overparametrized neural nets are out here in this regime. They've got way too many parameters than what we need to fit the training data, but those extra parameters can be used to generate a nice smooth fitting function that generalizes well to unseen data as well. So there's a very simple example in this paper of Belkin where he says, let's suppose we're just doing one-dimensional data fitting. We've got X here, we've got Y here, and we're trying to draw the class of functions that we're fitting from are piecewise linear functions with just two pieces. There's a single hinge at a random point between these two pieces. And so I've got to define a function that's a linear combination of these hinge functions to go through the red dots. So first of all, if I've only got 3 of these hinge functions to work with, I can't do a very good job at fitting the red dots. If I've got 30 of them to work with, I've got enough of them now that I can perfectly interpolate the red dots, but you can see that's not something that will generalize very well. In between the red dots, it's zooming off and doing weird things. So, this doesn't generalize well. But if you then take a massively overparametrized model with 3,000 of these functions, you've now got something that actually fits, that can fit the observations very smoothly. It can perfectly interpolate the observations, can go through them all the red dots, hit them bang on, but in between the red dots, it's also staying pretty smooth and giving us a credible interpolant. So that's the idea of sort of modern overparametrization.
And what's the explanation for that? What's your explanation for that phenomenon?
Well, here, what we're doing, that's several lectures in itself. I'll try to touch on it in the next few slides. I think I'm only going to be able to get up to the end of discussion of neural nets, but that's fine. You can read the rest of the slides later on. But what we're doing here is from this very rich parameter space, we're looking for the one with, say, the lowest average second derivative squared over that space. So we're, among the huge number of interpolating solutions, we're deliberately picking the one with the best smoothness. Okay. And it turns out, and this is where your question is important, it turns out if you do something more naive than that, if you just run a gradient descent approach, often it ends up at a smooth solution. That's what I'm going to try to explain in the next few slides. I think I'll skip this one. So I'll just try to get to the end of this section, and I'm going to go into some stuff that's in Belkin's paper, his review paper that he just posted on arXiv, I think maybe a week ago, maybe 2 weeks ago, that sort of explains a little bit about why overparametrized neural nets are finding these nice smooth solutions. So he starts off with linear regression. So let's just take a linear regression problem. We've got a bunch of points xi and rd. We're trying to fit a scalar output using regression. And it turns out that the underlying model is linear. There is the yi's are a linear function of the xi's with coefficient vector beta star. There's a little bit of noise added to all of them though. So we've got these epsilon I noises. But here's the important thing. The dimension of the xi's, the space that the xi's live in, is bigger than the number of data points that we have. So this is an overparametrized model, okay? The number of parameters beta is bigger than what we need to actually fit the data. And in fact, there are going to be infinitely many choices of beta. There's an entire affine space of betas that will actually interpolate the data, okay? Now, aesthetically, it might make sense to pick the beta among all those interpolating betas. It might make sense to pick the one with the smallest 2 norm. And you can show this sort of very classical result in linear least squares is you can identify this minimum norm beta by solving this regularized, Tikhonov regularized least squares problem, but then driving the regularization parameter to 0. If you do that, you'll end up at this interpolating beta. So that's been known for many years. And that's a sort of simple exercise in linear algebra. And in fact, people in machine learning have gone back to looking hard at this problem. There's a paper in Proceedings of National Academy by Peter Bartlett and co-authors that sort of examine exactly this problem and sort of make the point that, you know, having too many parameters, not necessarily a bad thing. But here's the interesting thing. You don't have to do this explicit regularization. You don't have to find the interpolating the lowest norm beta by setting up this regularized problem and solving it for some small value of epsilon. If you just take the original least squares model and run gradient descent on that and start from an initial point of 0, it will automatically give you the minimum norm solution. So let me convince you why that's true. Here's the problem we're trying to solve to get beta int. We're trying to find the minimum norm solution among all of those that fit the data. Now, that's a quadratic optimization problem, quadratic objective, linear constraints. So I can just use optimization theory to write down the optimality conditions. And the optimality conditions say that the optimal beta is just a linear combination of these xi's, okay? It's just a linear combination of the xi's. So what that means is that if this is the blue manifold is the set of all interpolating betas. This is a very cheesy, tiny example. But any point on that blue manifold, any beta on that blue manifold will exactly fit the data. The minimum norm solution is right here. But it turns out if we start from 0 and run gradient descent on this function with no regularization term on the beta, all I'm doing is taking the least squares objective and running a gradient descent algorithm. Every step, every gradient is going to be a linear combination of the betas. So I'm going to have to end up at this point because the linear combination of the betas will confine me to staying on this red line. And so when I run gradient descent, the only point I could end up with is this one here. And this is the beta end. This is the one I look for, okay? So this is this kind of remarkable convergence of interest between trying to find the minimum norm interpolant and just naively running gradient descent. It automatically goes to the right solution. And that's not just gradient descent. If I run stochastic gradient descent on this model, where I just approximate the full gradient by just a few terms of the gradient, exactly the same property will hold. Stochastic gradient will converge to the minimum norm interpolating solution. And moreover, it will do so at a linear rate. Okay, that's sort of another story. So this is the point I want to make. And you might think this is a trivial problem. Okay, least squares. We've known about least squares since Gauss 240 years ago. But it turns out this is relevant to what's going on in neural nets. And in the last couple of minutes of the talk, I'll try to give you some idea of why that's true. So, okay, so in certain neural nets, basically they boil down to being a problem that's very close to that very trivial least squares problem that I just told you about. Now that sounds crazy, right? Neural nets are these incredibly complicated, non-linear, non-smooth objects. But it turns out that in certain limits, neural nets behave a lot like linear least squares. Okay, so what is the setting that makes neural nets behave like linear least squares? Well, I can't talk about general neural nets. I've got to talk about some very specific neural nets. And these are nets where the second last layer has a large width, which we'll call M, and that the output of the neural net, the Y value, the label that you're outputting, is a linear combination of these outputs of the final layer. So we're talking about neural nets where you've got a very wide layer, width M here. you've got all kinds of stuff going on below that. You can have multiple layers, some of them wide, some of them narrow, all kinds of stuff. You got X going in at the bottom. And then at the top, you take a linear combination of these M outputs to get your Y as the output, okay? So the key is wide final layer, linear combination of the last layer. So what you can show, you can think of this first part of the neural net, you can as being a transformation of X to some other data space. So the input feature vector X, you can lift that, you can do a feature map to another data space by using this function, which is a derivative of the second last layer with respect to all of the weights in the neural net. So W is all the weights that are used to get you to that last layer, okay? So in other words, you're doing a map from X to some other space, which is implicitly defined by the neural net. This feature is called, this process is called a neurotangent kernel. And the interesting thing is that under these assumptions, that map is almost linear, okay? The map of X, sorry, the map of W, okay, this map here as a function of W is almost linear. That's the surprising thing. And so you can think of the problem of training the neural net as basically doing, I'm gonna have to jump over here, basically doing regression on this model. You've got N training points, N outputs, and you're trying to select the weights in the neural net to make the training points match up with the appropriate output. So you've got to solve a least squares problem to do that. But because of this linearity property, because this is almost linear in W, the training problem is pretty much a linear least squares problem. And therefore, it has all of those beautiful properties that I said. If you run gradient descent on it, it's going to go to a nice solution. It's going to go to a minimum norm sort of interpolating solution. And those minimum norm solutions have nice generalization properties. And so that's what's going to cause it to behave well. Among all the possible weights that would fit the data, it's finding one that sort of has a minimum norm, that has this sort of nice property. So I've had, unfortunately, for lack of time, I've had to skip over a lot of the details here. I've got a few details in these slides that I've skipped that come right out of Belkin's paper that explain why this mapping is almost linear. And this hasn't solved the whole problem. I'm going to skip the last part of the talk. This doesn't solve the whole problem because real neural nets do not have the structure that I talked about. So there's still a lot of work to do at sort of taking this theory and making it apply to more practical neural nets. But at least an explanation is kind of starting to emerge. And I really recommend Belkin's paper to you. We studied it in a reading group here, so I've got a bunch of slides that kind of break it down a little bit. I'd be happy to share those with you if anyone's interested. So I'm skipping over the last part of the talk. Let me just jump to the conclusions. You're welcome to read those slides if you're interested. Let me just say that there are abundant connections between optimization, control, and learning. I've barely scratched the surface. I've just kind of highlighted a few things in this talk. There are many more that I could possibly summarize in an hour or even in an hour and 5 minutes. Why is that? Why is there so much interesting interaction? It's because these three areas provide a lot of sort of complementary perspectives on many of the same problems. Not only complementary perspectives, but a lot of complementary tools. They all bring a set of tools for analyzing, formulating these problems and actually solving them algorithmically. So I think that's why there's so much interaction. And then just going back to this thing that I mentioned, I think once we start doing these things in an economics context, it's going to bring back a whole bunch of new tools and sort of open, I think, a whole new frontier of interesting work. And most of that lies ahead. So thank you. I'm very sorry I went over. I hate it when people go over. So I'm sorry I did that to you. But I'm happy to take any questions.
I have a question on the new perspectives of non-convexity. Is this just for unconstrained optimization, or do these also hold for constrained optimization?
Yeah, good question. No, they do hold for some constrained contexts as well. Some of these low-rank matrix problems are actually non-negative matrix factorization problems, so that they have positivity constraints on the matrices as well. So so they have constraints, and these AC power flow problems, the same thing. I'm trying to scroll back to that slide, but problems in AC power flow, the non-convexity actually comes in the constraints. They actually have a convex objective, but the feasible set defined by the constraints is non-convex, so they have to deal with that. So the answer is yes, they're for constraint problems as well.
Do you also know maybe if in the MPC optimization context there are kind of results for like the non-convexity?
No, I don't know anything about that. Yeah, and I know there's nonlinear MPC, and I know that they're generally non-convex. The input function is a non-convex function of the current state. But I don't know of any results trying to find conditions under which that's an easy non-convex problem. That would be an interesting thing to look at, for sure. Yeah.
Hi, could I ask a question too?
Yeah. Nicholas, how are you?
Hey, how are you? Hello, Steve. Thanks for the very nice talk.
I look forward to your talks.
Well, thank you. Yeah, tomorrow, as you advertised. Thank you for that.
Yeah.
So I had a question, which is, you mentioned at some point some applications in industry that you worked on, and the optimization problems that come up, like in actual life in industry, they tend to be a lot more complex than the ones that we study, in university oftentimes. So I was wondering, could you comment on which methods, in your experience, still work in the real world? Like, for example, trust region methods, I would expect work quite well in the wild. Is that also your experience? Do you want to comment on that?
Yeah. Well, I only have limited experience in industry, so I have to trust the experience of particularly my engineering colleagues like Jim Rawlings, and then there's Larry Biegler and Andreas Wachter and Victor Zavala from the Carnegie Mellon Chemical Engineering Department. They work a lot with industry applications, but they still also do fundamental work in optimization. So, for example, the IPOps, nonlinear programming interior point code, came out of that group, Larry and Andreas Wachter. And, they use that all the time on industrial problems. And it's it's a theoretically rigorous nonlinear programming algorithm, and it works well in industrial problems. So, so I sort of trust their experience in that regard. Ignacio Grossman, of course, has spent a career doing using integer programming and discrete optimization in chemical engineering contexts, and I think he's been very effective at solving a lot of practical problems for industry. So I think the gap between traditional optimization and industrial optimization is not that large. There are people working at the frontier who contribute greatly to real algorithms, real software that's theoretically valid, rigorous, but at the same time is strongly motivated by solving these very dirty, difficult, ugly industrial problems. So I think the gap isn't all that wide in a lot of these areas.
Thanks.
Hello, thank you for your talk. I want to ask about the part you used neural network to imitate the MPC. How can you guarantee the constraints and stability of the system for this case?
Yeah. Okay, I guess I'll share again. No, I won't bother. Okay, so we do have a theorem about to say that if the neural net gets within a certain distance of the MPC solution, we still have stability. So there's a theorem about that. It's just kind of a standard theorem that just quantifies the perturbation and says how big the perturbation can be while maintaining stability. Now, as for constraints, we don't do that very carefully. We just say that if the output of the neural net falls out of the range that we want if the input produced by the neural net falls out of the range of allowable inputs, we just clip it to the boundary. Okay, so that's just a heuristic. So I think in principle, you could figure out how to incorporate the constraints better, but it's potentially harder. I mean, I don't think there's anything to stop you putting constraints into the LQR subproblem so that you could put in state constraints and input constraints into that problem. We didn't do that in this application. It typically makes that piecewise affine map more complicated. So you might need a lot more training examples to come up with a reasonable neural net approximation. But I don't think there's anything to stop you from doing that. Yeah, easy to solve. There's a question in the chat. By easy to solve, I mean finding a useful solution to the non-convex problem. And that usually means finding a global solution. But I think more subjectively, a solution that in the context of the problem is useful to the practitioner would be good enough. And usually they're looking for a global solution. So usually that's the same thing. Not a local solution. Just a generic local solution usually isn't good enough. We already sort of knew how to do that. It's not good enough unless you can prove that in that application, the local solutions are all global solutions, which sometimes happens in matrix optimization.
I also have a question. Many thanks for your nice talk. So I'd like to ask you your general opinion on the deployment of second-order methods for training neural network. I was there at your talk in Braunschweig 3 years ago, if I'm not wrong. And there you discussed the Gauss-Newton-based method with the conjugate gradient. Right. But now you seem to be advocating instead the nice property of stochastic first-order methods, right, in your last slides. So yeah, I was wondering if you change your mind, also because this is a yet open question in the community, and a lot had been said and a lot is still unclear. Many people claim they don't generalize well these methods. They find, so to say, not so nice solutions, I don't know how to put it. And also, it's not clear whether we can pay the price of these more expensive iterations for the state-of-the-art size of neural networks. Right. It seems they work nicely on small, medium scale network, but they haven't proved to be strong enough to beat the first-order methods.
So I have thanks for the question. So when I talked about, I did a lot of work over the last 4 years or so on methods for general smooth, unconstrained, non-convex optimization with complexity guarantees. And I was sort of focused on Newton conjugate gradient type methods. I didn't have neural networks in mind as an application for that. I wasn't advocating those for neural networks. So I was more interested in, non-convex matrix optimization problems, possibly non-convex robust statistics problems where instead of least squares, you're using some sort of non-convex fitting function. There are the kinds of problems I had in mind. I don't think anyone seriously anymore is suggesting that you use Newton conjugate gradient to solve neural net training. So I was never advocating that. But although people have tried using, approximations to some sort of second-order information, but I think still that's not very successful. So that's why I was going back to focus on stochastic gradient and variants of that, because that is what people really do in practice, and the interest is in applying that to neural net is in understanding A, why it's converging to a global minimizer, and B, why the solution that you find by doing that does seem to generalize well, to unknown data. And that's what these people like Misha Belkin, Montanari, Sasha Rocklin, Peter Bartlett, all these very distinguished people in the machine learning community are putting so much effort into trying to understand analytically why that's true. I mentioned Alan Zhu as well, my colleague Yingyu Liang here at Madison. They really want to understand why this very basic method on this very difficult problem seems to be working as well as it does. And they're making progress. There's still a big gap between the theory and the practice, but these very interesting perspectives are emerging. And I tried to sketch one here. If I'd had another 10 minutes, I could have gone into a little bit more detail about Belkin's particular perspective, but they're coming up with these very kind of original complementary perspectives as to why this is happening. I think this is one of the big unsolved problems in data science is the unreasonable effectiveness of neural nets, and not only that, but the unreasonable effectiveness of stochastic gradient applied to neural nets. I think that's sort of one of the grand challenge problems in data science.
So just a final question on along these lines. So you don't think that the field overfitted somehow, so to say, in building this architecture such that the first order methods were working nicely, so to say? Because at one point I also asked myself whether this was the case, and maybe the whole field moved in designing architectures that were easy to be optimized with first order, stochastic first order methods, and there is still a niche on undiscovered and potentially powerful structures that aren't yet discovered because people are not using still these more advanced numerical methods, so to say.
Yeah, certainly it's not unreasonable to think that there might be some structure or approach out there that's waiting to be discovered, some paradigm change. But it seems likely that you are going to, whatever sort of classification or regression technique that you use, it is going to need to have a lot of parameters. I think it's going to need to be able to approximate high complexity functions. I think that's always going to be true. It's crazy to rule out that there might not be something out there that no one has spotted yet, that might do an excellent job in certain applications, better than neural nets are doing now, and might give rise to a whole bunch of new issues in terms of optimization training that maybe different algorithms will be better suited to than just gradient descent. So you can never rule that out. But by the same token, you've got hundreds of people looking at this very, very intently, and they haven't found it yet, if there's something better than neural net. So you can't rule it out, but it's becoming less likely as time goes by, I would say, that there's something we haven't spotted yet.
Many thanks.
Let's see, there's a question in the chat, minor question regarding the NN approach. Did you compare process execution time? Yeah. Right, no, we didn't compare against a traditional explicit NPC, mostly because for a problem of that size, we couldn't see a reasonable way to approximate the explicit NPC law. So no, we didn't do that comparison.
So I thank you for the nice talk. I have one question about the implicit regularization. So basically, some of the algorithms that are used to solve the training converge to a certain solution. So you're basically selecting one solution, which is the one with minimum norm. Yeah. Which also correspond to some properties of the model that generates the data, which can be smoothness. So basically, right, it works better because you are
yeah, the algorithm seems to bias you towards solutions which have a certain regularity property that generalizes better.
Yeah, so this seems to me a little bit like we know that the initial model is smooth, and so we select a solution which is smooth, is it possible to choose a different regularization if you know something else about the model?
Well, you can always explicitly regularize rather than implicitly. So you can always add terms to the training loss that will enforce the kind of regularity that you're looking for. It makes the training more complicated because typically suddenly you have a more non-smooth objective. But that's always an option. The weird thing about neural nets is that, and about implicit regularization, is you don't have to do that. You sort of get that for free. But yeah, if you're looking for other properties, like I know people are interested, for example, in neural nets that have low Lipschitz constants because they tend to be more robust. And so there's less of a blow up of the data as it moves through the neural nets. So I think for that, they sort of put extra constraints on the training, as I understand. I don't know this area well at all. But as I understand, they put some extra constraints on the training to make sure that the weights sort of stay in a certain range and so on. So you can do that sort of explicit regularization and not just rely on implicit, I guess. That's one example. But there might be other properties that you have in mind where you know, you can always do them explicitly, but trying to prove that whatever algorithm you're using will achieve the same sort of regularity implicitly is going to be a whole new ball game.
Thank you very much.
And I also have another question. So how realistic is actually the assumption of PL globally? Because to my understanding is something that it could be realistic to have locally, but not globally. And also along these lines, would you think it would be worth it to also make analyses that are not global, but focus more on like the local properties of our problem structure, which might be actually stronger than what we have on a global.
Yeah. So this is a very good question. I can sort of talk about it specifically in the context of neural nets or overparametrization in general. Maybe I'll just share my screen again very briefly. Let's see. Okay, there's a blank screen. Good. So some of these papers, like the ones by Alan Zhu and Yingyu Liang, showed that if you have a single hidden layer neural net and you start from a random point, that it's always close to a solution that perfectly fits the data. And so what seems to be happening is that you've got this very complicated manifold of solutions. And as you increase the overparametrization, this manifold basically fills the ambient solution space. And so what this means is that if you start at some random point in a space, like here, you're going to be very close to a solution. No matter where you start, it's going to be close to a solution. And so it would be enough to prove that properties like PL or whatever don't necessarily apply globally, but just apply in some neighborhood of any random starting point. That would be enough. So that coupled with a space filling property would be enough to prove that you can get from a random starting point to a solution with high probability using a limited number of iterations. Okay, so I'm actually starting 3 years ago, I started doing experiments with this, and we're still doing them now, with neural nets of a certain depth and width. What is the nature of this curve of solutions? In other words, can you prove how densely this curve packs the space as you increase the dimension? And we've got some results about that, as a function of the width, as a function of the depth. We're starting to get some results about just how densely does this curve fill the space. And that will give us some information about how big a neighborhood do we need to be able to prove this PL property in? Okay. If we can show that to high probability, a random starting point is within a certain distance R of a solution, then we only need to be able to show that PL or whatever nice property we use holds to within holds in a 2R radius of any starting point. It doesn't need to hold globally. So that might address your question. And I think similar considerations are going to come up in any overparametrization context. Once you've got this, you know, entire manifold or subspace of solutions, it sort of takes away the need to prove global properties, particularly if it fills space like this, or particularly if you've got a way of, more generally, you've got a way of finding an initial point that's close to a solution. Then you only need to be able to prove sort of local PL type properties.
Mm-hmm. Many thanks.
That's a good question.
Thanks. And okay, just the final question. And what about the deployment of some kind of continuation methods to, so to say, start from a smoother landscape and then slowly transforming it back, so to say, to the original and hard to solve scenario that we would like to address.
Yeah, so people have certainly done that. They've done that, for example, in molecular conformation type problems where, I guess I'll share my screen again, where you've got a lot of local minima that are with high barriers between them.
Mm-hmm.
So people have done this thing of starting out with a smooth version of this curve where you average the curve convolved with a small window. So you average the curve over a window and you get something smoother, but that has its minimum in sort of the same place as the global minimum, which is right here. And then you gradually deform that into a curve that becomes more and more non-convex. And hopefully you can trace the solution to this minimum. So yeah, certainly it could be interesting to do that. I'm just trying to think if any of these data science contexts, whether that would be a good thing to do. You can imagine it being interesting in nonlinear model predictive control, for example. If you started with an LQR problem and gradually deformed it to a nonlinear plant rather than a linear plant, that might be a way, at least heuristically, of getting you to a global solution. But probably would be hard to prove things about that.
Mm-hmm.
But certainly that's something you could consider, yeah.
Many thanks.
Sure.
Are there any questions from the audience?
Just about dinner time for you guys, isn't it?
Well, it's still 5:30, so
okay, that's
it's
pretty
still a bit early.
I'm still drinking coffee now.
Yes.
10:30. I mean.
Yeah. Yes. Well.
Okay. So, are there any more talks today?
No. Today we end here, and tomorrow we will restart. I believe at 9. And yeah, we are going to have the question answer session with Marco Campi, and then in the afternoon the talk from Nicolas Beaumal, and yeah, and then we will finish the summer school.
Great. Okay. Well, I'll try to come to some of the afternoon sessions.
Sure.
Because that's morning for me.
Yes. Yes. Right.
That's on the same link, right?
Yes, always the same link, or in YouTube. Yes, if you find in YouTube the various lives. Then
okay.
Yeah, many thanks, Stephen, for the
sure. Thank
talk.
you for the invitation. Looks like you guys have done a great job with organization.
Thanks a lot. Thank you.
All right.
Yeah, see you tomorrow then.
Enjoy the last day. I'll see you tomorrow.
Many thanks. Bye.
Okay,
Thanks a
bye-bye.
lot.